Okay, hi. Today we're moving to the second dimension, and we're going to study linear two-dimensional systems. And we'll see how, once we are in two dimensions, we are already getting new phenomena of the dynamical systems, new possibilities, namely oscillations. And today we'll stay with the linear systems. First of all, it's a more simple case, and second of all, this will give us the tools with which we will treat the nonlinear systems. So the general form here will be this. And there should also be initial conditions of x0 and y0. And the first thing you would do when given such a system would be to find the fixed points, right? So you would set x dot equals 0 and y dot equals 0. And then you would get one or even more fixed points. And we go to the most simple case of the linear 2D systems. That's the homogeneous case. So this means that we have x dot equals ax plus by, and there is no constant that is added here. This is why this system is homogeneous. And y dot equals cx plus dy, where d is a constant. Maybe I should choose different letters here. No, we'll stay with d. D is just a constant here. And of course, we're given x0 and y0. So first thing we know is that 0, 0 is always a fixed point. And except in pathological cases, it will also be the only fixed point. So what does it mean, the only fixed point? It means that, what does it mean a pathological case? A pathological case is a case where the parameters are 0. So x dot equals 0 and y dot equals 0, and any point in the xy space is actually a fixed point. So once we have the fixed points, we would like to know something about their stability. So in order to do this, it's more convenient to use the vector form or the matrix form of the equation. And we just write the system as a product of matrices. So this is a vector xy, and I have a dot over it, which means that both its components are differentiated with respect to time. And then I put my parameters inside a matrix that multiplies from the left the vector that describes my system. And an alternative way to write this would be to write the vector x. X will be defined as xy. So the vector x dot is equal to a times the vector x. So this is the matrix form. then we would have our initial condition, the vector x at 0 is equal to some vector x0. And we'll see how the properties of this matrix A with these components that are actually the parameters here will determine the behavior of the system, the stability of the fixed point, for example. And when I say the properties of A, specifically I mean the trace and the determinant of A. So it's pretty simple to know something about the behavior of the system. We'll see how all we need is the trace and the determinant. Okay, so I start with an example. Okay, we have a system of two variables, two quantities that change with time, and it will give us complex behaviors depending on the conditions. And of course, this is a good description of a love affair. So we are looking at one of the most famous love affairs, Romeo and Juliet. We have the feelings of Romeo and the feelings of Juliet. They can be positive or negative, and they can assume different values. And we start with a simple case where the feelings of Romeo only depend on Juliet's feelings, and Juliet's feelings only depend on Romeo's feelings. This is our system. Okay, so if we want to interpret this, we'll see that Romeo will love Juliet as much as she loves. Well, if she loves him, then he will increase his love for her. Okay, if she hates him, he will increase his hate for her. Juliet, on the other hand, hates Romeo if he loves her, and loves him if he hates her. Okay. And we'll also pick some initial condition. And start to check what happens with this system. So first of all, we know that we have a fixed point at 0, 0. R star J star equals 0, 0. So this means if no one feels anything, then nothing will develop. They will remain indifferent to each other. And now, in order to see the general behavior of the system outside of this fixed point, we will try to consider what we call the phase plane. So the phase plane will be J versus R. And when you think about the system, you see that for each coordinate, Rj, on the phase plane, the system gives us a vector, okay, a vector R dot J dot that describes where it will go and with what force, you could say, okay, what driving force. So if I pick our initial condition, sorry, I said 1, 0, but I wrote 0. No, this is the initial condition. Okay. If I pick the initial condition here, then this is a coordinate. And for this coordinate, I can match the vector that marks the change. This is the same thing that we did when we had the x-axis and x dot, and we marked arrows on the x-axis. So now these are arrows on a plane, vectors. So for this coordinate, r equals 1, so j dot equals -1, and j equals 0, so r dot is 0. So this is just a vertical arrow going down. Okay? Then I can pick a coordinate around here. So both r and j are no, r is positive and j is negative. So if r is positive, j dot is negative. This is a component. And for a negative j, r dot is also negative. So I can construct my vector for this point, just very roughly. And I keep doing this for different places on the phase plane. Okay, so phase plane, that's a definition that you should know. The phase plane over here, I have this. So r equals 0. So there is no j dot. It's just a horizontal vector. And j is negative, so r dot is negative. So it's pointing to the negative direction. I can keep doing this, and what I get is basically this kind of vectors. I'm not going to prove it, but this is actually a circle that's forming here. So this is actually a very special case of two-dimensional linear systems where we have closed orbits. So for any point on the phase plane, as an initial condition, the system will close in orbit. It will just oscillate around this orbit. So we have a fixed point here. If we start in the fixed point, we never go anywhere. And for any point on the phase plane, we have a closed orbit. Yes.
You drawing the vectors and the r dot and r positive in the same direction.
Yes.
Something you decide, or is it?
Well, r dot is the change of r with time.
Can grow when r goes negative. Depends how r is defined.
What do you mean?
R can be defined as minus some a multiplied by r, and then when r is going.
No. So over here, it's not defined. This is a definition. This is the system that we're dealing with. Yeah, we'll move to a more general case later. So this is a very special case of closed orbits. And it already shows us something that we could not get in the 1D systems, which is oscillations. So here we have oscillations of different amplitudes, and the amplitude depends on the initial condition. Okay, so this picture, without the individual vectors that I drew, I'll cross them out. So this picture that shows us the fixed point and the trajectories here is called, this is our phase portrait. We had a phase portrait before, but this is what it should look like in the 2D system. Yeah. And the phase plane is the RJ plane.
Okay, so in the phase plane we draw the phase portrait.
Yes, exactly. Okay, if we want to interpret this, then we can say that we start where Romeo loves Juliet and she has no feelings for him, but then she starts hating him for loving her. And eventually, Romeo stops loving her. They both hate each other. But then, when Romeo hates her, Juliet starts loving him. And then they enter this state. Eventually, they will both love each other, but that will be short-lasting, and they will be trapped in an endless cycle of love and hate. It's pretty grim. And so we move to a different system, and here we will have Romeo. I will call his character here as impulsive. Okay, there is some parameter S that controls how much is uh, affected by his own current feelings. So if S is positive, then it means that if Romeo loves Juliet a little, then he will this will escalate and he will love her a lot. And if he hates her a little, he will hate her more. And Juliet, uh, she'll be kind of indifferent, maybe, or I don't know how to call it, but okay, this is a negative term. So once she loves him, she kind of becomes careful and stops loving him. Or if she hates him too much, then she returns to indifference. So here, um, actually, the equations are not coupled to each other. This is another simple case, and we can solve each equation on its own. Okay, so we can write RT equals R0 e to the power of st, and J of t equals J0 e to the power of minus t. So, like I said, the feelings of Juliet will eventually decay. The feelings of Romeo will only get more and more intense uh, to whichever side. Again, 0, 0 is always a fixed point. And then we want to move on and try to get the phase portrait for this situation for different values of f. Okay? Yeah. Excuse me. Is a circle? Well, yeah. The circle is a kind of. It's not a fixed point, but it's an attractor. No, it's not an attractor. We call it an orbit. So the system can stay on this orbit. Yeah, there is only one fixed point, and there are closed orbits. Okay. So I said we want to have the phase portrait for different uh, situations here, and the situations are defined by the values of s. So I start with s equals minus 1. So here Romeo is also a kind of different. Maybe someone from psychology can give me a better term here. So the decay of their feelings will be equal. Will have an equal rate. I have J versus R, and anywhere I start, the decay of both their feelings with time will be equal. So I will just go in a straight line to the center. I draw several representative trajectories. Obviously, this whole area is filled with them. And they have the fixed point, and we can see, based on this actually graphical method, that this is a stable fixed point. We could also tell it from the values of the exponent here. And we call this fixed point a star. So 0, 0 is a stable star. Yeah. To this, because s equals minus 1. So both equations look the same. Okay? Yeah. Yes. we'll get to more to finer definitions of stability later. It's
Or I can have an orbit if we move a little bit.
yeah. If you move a little bit, then you go to the orbit. So I would call this Lyapunov stable. No, actually no. Maybe it's Lyapunov stable. Yeah, I guess so. We'll see the term later. Okay. Okay. So this is a stable star, and you'll see later why we call it a star, just because it has these straight lines coming out of it. And we could also, in principle, have an unstable star, and the situation would look just reversed. So this would be an unstable star with all the arrows pointing out. Of course, we can't have it in this system because Juliet always has her feelings decaying. So that would be an unstable star. Okay, so the next thing I want to consider is S smaller than -1. So Romeo's feelings decay faster than Juliet. So for any point on the phase plane that I would take, of course they have the fixed point at 0, 0. This is a full circle like we had in the one-dimensional system. A full circle marks a stable point. So for any point I take here, Romeo's feelings decay faster. This means that my vector would first go towards r equals 0, and the kind of the onset of Juliet's decay in her feelings will be later than the onset of Romeo's decay. So this is why all the trajectories will kind of curve towards the j-axis, okay? Because first r gets to very low values, and then the decay in j is seen. And we should also consider what happens on the axes. So if j starts at 0, then there is no change. So we just have straight lines. If r starts at 0, then only j changes, and we have straight lines. Okay, now this is this type of fixed point is called a node. It's a stable node. Node is the more general case to which the stars belong. Okay, so a star is in fact a type of node. But in this course, when I say node, I will usually mean a node that is not a star and not any other special type of the types that we will see later. Okay? So node is the general term for an attracting or a repelling fixed point. But here we will use it for a fixed point that does not belong to any special case. Okay, in principle, we could also have an unstable node if both these prefactors of the exponent will be positive. So in an unstable node, we'll just have the arrows reversed, okay, coming out of the fixed point. So actually, here I should have had an empty circle, and for an unstable node.
When only one is positive and one is negative, do you call it stable?
No, I call it unstable. We'll see it in a moment.
Just enough, just one of them is positive, that it will be unstable.
Yes. Okay, so that will be an unstable node. but then it won't be called a node. You'll see in a moment. No, okay, first another case where S equals 0. Yeah? S equals 0. So what happens here? R does not change with time. So for any point on the phase plane, the dynamics will keep me on a line with a constant R. If I start here, then I just go down on a constant R with a decay in the feelings of Juliet. If I start here, again, decay to J equals 0. So I can fill the phase plane with these lines that go toward the R-axis. And the R-axis is a line that is made up of fixed points. I call this a line attractor. And there could also be the opposite case of a line repeller. But that term is less important. So this is line attractor. It's made of fixed points. We'll see the term for the stability of these fixed points later. But you can imagine that if you are on a fixed point and you move a little to the right or to the left, you will just stay there. Okay? Other cases that we will consider. Well, I hope you understand that here, if I would have chosen S between 0 and -1, the curvature will be different. Okay? So if S is -1/2, for example, then the Romeo's feelings decay more slowly than Juliet's feelings. And this means that for any point on the phase plane, Juliet's feelings decay first. I mean, decay more quickly in the beginning, and only then we start to see the decay in Romeo's feelings. So here the value of S just determines the curvature, and the important thing is that it's negative. Another case that we must come to know is the case where S is positive. Actually, I started with this. I said that Romeo is an impulsive character. So for a positive S, move it where? From here? Yes. For a positive S, let's, okay, for a positive S, Juliet's feelings always decay. So if I take the J-axis, then R0 is just 0, there is no change, and Juliet's feelings will decay on the J-axis towards 0. Okay? But if R does not start at an initial value of 0, and S is positive, then R will grow to infinity with time. So if I start here, Juliet's feelings will decay, but Romeo's feelings will increase in their intensity. And same here. and the same here, and the same here. So I have here 0, 0 is still a fixed point, but it seems that I'm running away from it, kind of repelled from it, except if I start on the j-axis. Okay? Exactly on the j-axis. On the r-axis, I also have the system running away from the fixed point. So this is, strictly, this is an unstable fixed point. I mark it with an empty circle. And the term for it is a saddle point. Okay? You can imagine a three-dimensional surface with these vectors actually marking the way that balls or fluids that you would drop on the surface would flow with time. So, and then this thing here will look like a saddle point, like a horse's saddle. So you might have the j-axis has things going down on it. It's a kind of curve that has everything going down here, but everything else has my imaginary fluid or balls going away from it. Okay, so I don't know if it's a very good drawing, but you also know what a horse's saddle looks like. Okay, so there are two special lines in the phase plane that relate to the saddle. We have the stable manifold. Okay, this is actually a line, but when you go to higher dimensions, a manifold could signify a line or a plane or a surface. So the stable manifold here, it's the j-axis. This is a line where if you start on this line, you will always stay there.
You'll get to the fixed point.
But you stay on the line.
Oh, yeah.
Okay, so it's a set of initial conditions R0, J0 such that they go to the fixed point as time grows, or generally x0 of t such that x vector goes to x vector star as t goes to infinity. And we also have the unstable manifold, which is here the r-axis. And over here, if you start on this line, you go away from the fixed point. So on this, when you consider only this line, the fixed point is unstable, just an unstable node. Okay, so this would be x0 of t such that x goes to x star as t goes to minus infinity. Okay, if you would run time backwards, then on the unstable manifold, everything will go to the fixed point. Okay, running time backwards is a nice trick. You'll see it later when we try to find orbits in the phase plane. Okay, so we saw different types of fixed points. We saw the line attractor. We saw the node, which includes the special case of a star. We saw the closed orbits, the fixed points surrounded by closed orbits, and we saw the saddle points. Okay, we have another type that we will deal with later, but first I want to introduce the types of stability that we are talking about. So we see here that it's not satisfactory to describe things as stable or unstable, because then unstable will include both a saddle and an unstable node or unstable star, and we know that the behavior here is qualitatively different because here we have this stable manifold that divides the phase plane into actually two basins of attraction, two sinks, you could say. So we want to have finer definitions of stability. So we talk about an attracting fixed point. And attracting fixed point, we say that this is a fixed point, well, a vector, such that, okay, all trajectories starting near the fixed point have x going to the fixed point itself as t goes to infinity. So this will not be an attracting fixed point, right? This will not be an attracting. This will be an attracting. And then we have the term Lyapunov stable. And Lyapunov was a scientist who contributed a lot to the field of dynamics. So this is the first of at least three terms that carry his name and that we will encounter in this course. So here we say that all trajectories starting sufficiently close to the fixed point stay close to it. Okay, so this is Lyapunov stable point. This is not Lyapunov stable. Okay. These points are Lyapunov stable, like I mentioned earlier. Right? If you are on a fixed point and you move sideways, you will stay there. Okay. If you consider one fixed point and you have a trajectory starting just next to it, to the right or to the left, the system will stay close enough to the fixed point that you are considering.
So
Yeah.
also the first one that we saw, that they circle around it?
Yeah.
Would this also be?
Yeah, I think I would call it the Lyapunov stable. And now I would like to make a table to classify different fixed points, different types of fixed points. So a fixed point can be attracting, this is not big enough. And it can be Lyapunov stable. And we'll try to put in our different fixed points in here. Okay, so fixed points that are both attracting and Lyapunov stable. We usually just refer to them as stable. There is also the term asymptotically stable. This comes from the fact that actually usually we have decay according to an exponent or to hyperbole, and actually the system will never really get to that fixed point. Well, it will decay asymptotically to it. And here we have the node star. A fixed point can be non-attracting, but still Lyapunov stable. So here is our example for that. So the fixed points here are not strictly attracting, because if you start just next to them, you won't get there. You won't ever get there. And we call these neutrally stable. And fixed points in a line attractor are neutrally stable. The line attractor is itself, the line as a line is actually stable. Okay, it's not neutrally stable. The fixed points inside it are neutrally stable. Fixed points that are not attracting and not Lyapunov stable, we call them unstable. We mark them with empty circles. And we have unstable nodes, stars, and also saddle points. Also FPs in an unstable line attractor. So we just call them unstable. And if a fixed point is attracting but not Lyapunov stable, so these are very special cases. And I can give you a case from one-dimensional dynamics where the one dimension we have is closed as a circle. Okay, so we call these half stable. We saw them, but the half stable points that we saw in 1D systems are not actually Lyapunov stable. They're not attracting. But when you close your phase space to a circle, then you might have this situation where if you start here, you need to complete a circle, and you're attracted to the fixed point. And so anywhere along the circle, you're attracted to the fixed point. But the idea is that it's attracting because for any point close to it, you will get to this fixed point as t goes to infinity. And all trajectories starting sufficiently close to it will stay close to it. Sorry, it's not Lyapunov stable. So they will not stay close to it for all times, but they will, when you look at long times, they will get there. Kind of, yeah. And then in nonlinear systems, we sometimes find other examples for this.
So also, if you do this circle, you might as well say that they're not always close to it, but eventually, you know what I'm saying? If this is your fixed point and this is, and you're doing those circles till you get close, then
Yeah.
in this case you would call it also attracting and not Lyapunov stable.
Lyapunov stable. Um,
For the same reason, because it's not always close to it, but just at this given time will it get there?
you mean a spiral that goes
Yeah,
into the
how would
fixed
you
point?
classify this?
A spiral?
Yeah.
It goes here
Yeah, no.
with the stable.
But the same way you can say, I mean, it's as you said about this, that it's not.
No, in a spiral, you get closer and closer to the fixed point.
No,
So
but you at some time you get like further.
no. Here, the spiral will be stable. The idea with with no Lyapunov stability here is that, yeah, you get farther away from the fixed point before you come back.
But also in spirals,
No.
You can go at least in the beginning a bit further.
No.
Yeah.
No, in a spiral, you just go inside. Okay, it's not going like this. You don't have these
so
things.
this you would classify as well as
This thing?
no Lyapunov stable.
Not Lyapunov stable, yeah. Okay, let's take a break of 10 minutes.
יש להם.
כן, הוא מורכב מנקודות צבע. אז היציבות של הקו היא לא מאותה קטגוריה של היציבות של נקודת השבט.
זאת אומרת, זה
כן, נקודת השבט הזאת היא מה שאנחנו קוראים stable. בכל נקודת שבט פה בתוך הקו היא מה שנקרא neutrally stable, אבל הקו עצמו הוא stable. אם אתה מביט על הקו, יש כביכול לכל נקודה רק שני טראג'קטורים שנמשכים אליו. נכון, כולם מתפרעים. כן, לא בגלל זה, כי הסטביליות שלהם ניטרלית, כי אתה יכול לזוז ממנה קצת ואתה תישאר שם, אתה לא תימשך אליה, אבל אתה לא יכול לזוז מהנקודה ולהישאר בה. אתה לא נשאר בה. אתה זז מנקודה אחת לשכנה, ואתה נשאר בשכנה.
האנליטיקל סולושן היה רק
אתה לא מתרחק לכל הקו בעצם. הנקודות על הקו הניטרליות, הקו הוא נחשב יציב. הוא לימוד שצריך לכל אלה.
דווקא מקבל משהו ששורש, אני מספיק שורש מדי, נהיה שלילי בסוף, ואז
הפרוג'קטורים לוקחים את דימנשן שלו.
היה השאלה הראשונה, היה למצוא פתרון האנליטי בלבד.
לא, זה שכן ככה.
רציתי קודם כל לשאול לגבי שאלה 2 ושאלה 1. אז מכיוון שאנחנו לא יודעים בצורך, אז אנחנו אומרים את המתמטיקה זה החלק האמיתי, לא את החלק המדומה?
אין דברים מדומים.
כי מבחינת אם נתייחס לזה ונגיד בתור, נגיד x r שווה נגיד ל-x בשלישית, זה כאילו תהיה זה הפספוס, כאילו לא לעשות כאילו...
כן, הרעיון הוא שמה שקורה מבחינה אפקטיבית בנקודת השבט הזאת הוא דומה לנקודת שבט שלמדנו, אבל מבחינה מתמטית היא לא אותו סוג של נקודת שבט. ביקשתי פשוט שתסווגו לפי ההתנהגות ולא לפי המתמטיקה.
זהו, אז אני פשוט לשאול באמת בעניין הזה, אז כאילו מה הכוונה בעצם לזיהוי נקודות בחלוקה? כאילו לא יודעת, כתבנו את זה בשיעור, כתבנו בסיווג סייבר פה,
critical ופיצ'פורק.
It will not go back.
פיצ'פורק היא הקלשון.
נכון, כן, שזה...
אז ראינו שלושה... ברגע שאת מסתכלת על דיאגרם של דיפרנציאציה, את יודעת מה זה, בין השלושה.
אוקיי, לפי הדיאגרם, מה זה?
לפי הדיאגרם. אז זה based on its properties and the appearance of the bifurcation diagram אותו לא על ידי ה-normal form. את לא צריכה למצוא פה את ה-normal form, אבל אם היית מנסה למצוא, היית מגלה שהיא לא מתאימה לשום מצוא.
עכשיו, בפיתוח טיילור, אתה רוצה שאנחנו נציב ממש את הנקודות, נגיד, שלח לפני, R קריטי, תמיד, איפה אנחנו חושבים לזכויות? כלומר, ההגדרה של קריטי זה
R שבו משתנה, או משתנה מספר נקודות שבט, או שמשתנה יציבות של נקודות שבט. בקטלו נוד זה R שבו הן נעלמות, בקלשון זה הזמן שבו הן מתפצלות, ובקריטי, לא, זה לא, ממש לא יכול, כן.
אז הכוונה היא ממש, בכיתה אנחנו לא הצענו את הערכים, זה ביטוי כזה שלי, A כפול, נגיד A הערך הנגזרת, כפול X פחות X
כן.
אז זה בין שנציב ממש את ה-R קריטי?
כן, זה יותר קל.
ממש אז כמה פחות, כאילו אם אני יודעת מה הערך בנקודה קריטית. אוקיי, עכשיו לגבי הערך בנקודה קריטית אפשר לבדוק אלו.
כן,
יש הרבה קריטיות בהרצאה קריטית, הרבה כאילו פיקס פוינט בארצות, כאילו R קריטי יכול להיות...
ב-R קריטי יש פיקס פוינט אחד.
אם יש לא לך אחד, זה לא...
כאילו, אבל נגיד, אני רוצה להגיד דוגמה בפרוקציה, אז כל זה... כאילו, נגיד,
לא, בדיאגרם של פרוקציה יש R קריטי שבו נגיד משום נקודות שבט וחוזרת לשתי נקודות שבט.
זה ממש נקודה, אוקיי.
אפשר לראות את האחד של
איך הדבר הזה נראה?
לוג, שתוסיף את זה ל-x, יוצא לך את החצי, יוצא לך פלוס ה-x. לוג של זה שווה ל-c ועוד c. פה היה צריך להיות מינוס, כי הפונקציה הקטנה הזאת היא 1 מינוס, כי 1 מינוס, אז מינוס לוג של זה מינוס לוג של לוג, פה זה היה מינוס, ואז אני מעלה בחזקת במקום לוג של החזקה זה לוג של חזקת k, והחזקת זה היה חזקת k משהו, אז מעלים את זה ל-x, ואז הוא חוקי, ואז עם האלגברה, ואז במקום כן, תמיד זה מינוס.
שורש נורא קשה לדעת, אני לא ראיתי שיש משחק שיש עד 4 סיכונים, ברגע שיש 2 ואז יש להגדרה מתארת ככה ובשש. אבל כשמגדירים שורש ומגדירים מספק, זה ממש קשה לדעת, כי זה ברגע שיש
למה תגיד את זה? אתה עושה שעה למטה, אז אומר לך, repeat all the process for... לא, עכשיו, בשאלה ראשונה. כי זה לא... בתיאוריה זה תקליד לפונקציה, אבל את צריכה לטפל בנתונים. יש מלא, כאילו בתיאוריה אתה אומר, אוקיי, טוב, אבל תציב הכל.
אוי, צריך להתאים את זה גם, צריך כל הסעיפים של השאלה.
לא, עשיתי את זה ככה.
רגע, אני לא חושבת שיש לי את הדף של זה.
היה קטע, לא, זה...
השאלות בכלל, כאילו,
So we looked at different cases for the 2D system that we considered, Romeo and Juliet. And now we move to a general solution for the 2D system. Okay, so if we have a system x dot equals a of x, then the solution will have the form x vector equals e to the power of lambda t times a vector v, where v, well, I'll just show it like this. V is an eigenvector of x, of a, and lambda is the corresponding eigenvalue. So V is an eigenvector of A, lambda corresponding eigenvalue. Excuse me?
A is the matrix.
A is a matrix like we had before.
So you can have a combination of eigenvectors.
Yes.
So you don't have to be just one eigenvector.
Yes, but this is a general form. Okay, no, this is a solution. So, yeah, when you would like to write, I'll write it later. The general solution will be a combination of such solutions. Okay, I want just to show you that this is in fact a solution. So I'm going to take this and substitute it for the vector x. Okay, this is just lambda times e to the power of lambda t times v. Right? E to the power of lambda t is just a number, so I can switch the order. Times lambda v equals e to the power of lambda t times av. Because lambda is an eigenvalue and v an eigenvector, I just switched to av. And since this is just a number, I can, again, put it here. A times e to the lambda t v. And this is my x. So I do have x dot equals ax, and this is a solution. Like you said, it's not the only solution. This is called an eigensolution for the system. And okay, before I move on to the general form, I would like to show how we find these v and lambda that are needed for the eigensolution. Most of you probably already did this in multiple courses. So first we are going to find lambda. That's the more simple task. And we'll solve the characteristic equation right? So our A is of the general form that I showed earlier. Now I'll write its components. So that A minus lambda I is a determinant of this matrix. So this is A minus lambda times D minus lambda minus BC. AD minus lambda D minus D lambda, I prefer this order, plus lambda square minus BC. and in the characteristic equation, this must equal 0. Now I separate the terms. I get lambda square minus lambda times a plus b minus bc equals 0. Sorry, minus ad, yeah, plus ad minus bc. So this is the quadratic equation that we need to solve in order to find lambda. And I want to point out that this is the trace of A, and I call it tau in this course. This is the determinant of A, and I call it delta, capital delta. So I have a quadratic equation where the prefactors are actually the trace and the determinant of A, and the solutions can be written using the quadratic formula. It's tau plus minus the square root of tau square minus 4 delta, and everything is divided by 2. So this is how we find lambda. We get this linear system with these parameters, and immediately we can substitute here and find the eigenvalues. The next thing we should do is find the eigenvectors, right? So now we know we have 2 eigenvectors, maybe, but a maximum of 2 eigenvectors. How do we do this? We just solve the equation AV equals lambda V. So to do this, I would define V with 2 complements that serve as the variables here. So I'll have A, B, C, D. Yeah.
Why suppose you hold only 1 lambda each?
Where?
Can't see it by chance. Well, x equals exponent.
Here.
Yeah.
So this is
With 2 solutions.
this is an eigensolution, and there are 2 eigensolutions. Yeah. This is just a solution. This is an expression that would solve that equation, and there are actually 2 specific eigensolutions. Yeah. Later I'll write them both in a combination, in a linear combination. Okay, so here you get 2 equations, and you can solve for U and for W and get, since you are given lambda, this is one of the lambdas that you found, then you can extract U and W out of these equations. So we know how to find the eigenvalues and the eigenvectors, and this means that we can get to the solution of the linear system. In the nonlinear system, this will not be possible, or at least not as easily. And now we will look at different cases that we have with these solutions. Can I move the board? Okay, so one is the typical case of lambda 1 not equal to lambda 2. So I got V1 and V2 are linearly independent. So any initial condition that I get, x0, a vector x0, can be written as a combination of these two vectors, c1 v1 plus c2 v2. And the evolution of x with time occurs independently for each of these vectors because they are eigenvectors of the system.
What is x0?
An initial condition. So x as a function of t is equal to c1 times e to the lambda t v1 plus c2 lambda 1 t v1 e to the lambda 2 t v2. So, yeah? These are eigenvectors of the system. Okay? So, each the system has two solutions, and each of these solutions is actually going along one eigenvector with an exponential profile in time. So now we are no longer actually interested in x and y directions. We're only looking at the eigenvectors, and the states along each eigenvector evolves independently of the other. We kind of decoupled the x and y and moved to the directions that are relevant for this system. Maybe I can draw.
You're talking now about real eigenvalues.
What?
You're talking about real eigenvalues?
Right now, yes. Okay. Also, I'd like to note that since this linear combination, okay, maybe I'll make a drawing to explain what I meant. I have a certain system with two eigenvectors, and instead of doing a complete example, I'll just assume here that lambda 1 equals 2 and lambda 2 equals 3. And I have two eigenvectors, v1 and v2. And what this tells me is that for each point that I take, what happens with time is that the component of v1 grows with an exponent e to the power of 2 times t, and the component of v2 grows according to this exponent. So I can draw these components, right? And actually, their relative contributions depend on the initial condition. Okay? So for example, for this initial condition, I would have so C1 will be larger than C2, and this means that this component contributes more than this component, and when I add them, I go over there. So at this initial condition, this is where the system will go, and once I reach a new point, then I can treat it as an initial condition, and I can have my components and I know where the system will go, kind of like here. And it's always evolving independently on each component. Yeah.
This is something that I don't understand. You showed that the eigensolution, the exponent,
Mm-hmm.
showed that each initial condition can be written as a combination of the eigenvectors.
Of the
But
eigenvector.
I still don't understand why
Oh.
x of t equals
Yeah.
what?
Yeah, sure.
I understand that they are independent, they evolve independently, but why the exponent says so?
So let's substitute this into the original equation. Okay. So I want to so x dot 0. I'll do this. So C1 V1 dot plus C2 V2 dot equals A times C1 V1 plus C2 V2. And I can write this again as C1 A V1 plus C2 A V2. And I can change this to be, I'll do it here, C1 lambda V1, C2 lambda V2. Yeah. So I can basically treat these as two different directions, okay, and ask what happens on each direction. And what I get is that on V1 I have an exponent that either grows or decays according to lambda, and on V2 I have an exponent that either grows or decays, and basically the system is decomposed to things happening on the direction of V1 and things happening on the direction of V2. Yeah.
Can you give some intuition when we will use left eigen vectors and not right? When there is a need to change to make a transformation?
Well, I could use right eigenvectors, but then I would write the system differently from the start. But
there is no simplification for the
I
left
don't think so.
or
No, I don't think so. Okay, I want to move on. Okay, so let's look at this for lambda 1 positive and lambda 2 negative. Okay. I would have two eigenvectors, and along the system will evolve along the first eigenvector according to a growing exponent. So I can already draw what happens for all initial conditions which have no component of V2. They can be defined only using V1. They are on the direction of V1. So these initial conditions will run away from the fixed point at 0, 0. The initial conditions, that are only defined by V2, they have no V1 component, only decay according to an exponent with lambda 2 in the exponent. Okay? And this already gives you an idea of what happens here. So if I start here, then this is actually a vector. This point is a vector, and it will reduce its V2 component according to lambda 2. So it will go over there, but it will increase its V1 component according to lambda 1. And similarly here, this has a V2 component, right? It has a V2 and a V1 component. So its V2 component will decrease, and its V1 component will increase with time. And this is a saddle point. So a saddle point has one positive eigenvalue and one negative eigenvalue. Okay, if both lambda 1 and lambda 2, are negative, so this is even simpler. So any point where we start will decrease its V1 component and decrease its V2 component as well. So points along the V1 direction will just decrease and go into the fixed point. Similarly for points on the V2 direction. And in the middle, everything will decrease its components and decay, and the curvature here will depend on the ratio between the two lambdas. Like we did before with Romeo and Juliet. Okay, and if both of them are positive, then we have all the arrows pointing in the other direction. So this is a stable node. Could be a star if they are both equal. And the complementary case is the unstable node. I won't draw it because we want to move on. Okay, so one of you asked before if I'm talking about real eigenvalues. So far, we were talking only about real eigenvalues, and now we'll see what happens for the special case where we have complex eigenvalues. So if you remember our equations for the eigenvalues, we had lambda 1 and 2 equal tau plus minus the square root of tau squared minus 4 delta divided by 2. So what happens if the expression inside the square root is negative? And we will actually get two complex eigenvalues where we define the real component as tau over 2 and the imaginary component as this. And the general solution is still it still holds. So x equals c1 e to the lambda 1 t v1 plus c2 e to the lambda t v2. But now v1 and c1 are actually complex numbers. Well, these constants are complex numbers. V is a complex vector. Each component is a complex number. But the important thing here is the dependence on t. So basically, we have c1 v1 e to the power of alpha plus I omega t plus c2 v2 e to the power of alpha minus I omega t. And each of these things can be written as e to the power of alpha t times e to the power of I omega t. And then I can decompose this into the cosines and the sines. So e to the power of alpha t, and I have here cosine of omega t plus I times the sine of omega t. So what this means is that for each direction, there will be some exponential growth or decay depending on the value of alpha. And it will be a growth for both directions or a decay for both directions because we have a single alpha for both lambdas. And aside from this growing or decaying prefactor, we will have oscillations going as the cosine of omega t, where omega comes from the eigenvalue. It's the imaginary part of the eigenvalue. This is the frequency of the oscillation. So you can imagine that we have oscillation along this direction and oscillation along that direction.
But each direction is two-dimensional.
Yeah.
The imaginary dimension. That means
Oh,
there are two directions.
well, we are disregarding here the one-dimensional. So we are disregarding the imaginary part. X is real.
X is real.
So all the imaginary parts have to balance out in order to give us a real result. So if you have oscillations and growth that precedes them, you will have a spiral, right? Oscillation on two directions and growth. If you have oscillation on two directions and decay, you will have a spiral going inwards.
No, that doesn't have to be the exact spiral. Can be shaped weird, right?
Yeah, it might be a little distorted. Okay, so this special case, which gives us, it's not a special case, it's a range of cases, gives us imaginary eigenvalues, will give us spiraling to the fixed point or out of the fixed point, depending on the real component of the eigenvalues. And this real component is just the trace over 2. I can say that in the first case that we saw with Romeo and Juliet, remember we had R dot equals J and J dot equals minus R, yeah? So if we would write this in matrix form, you'd have Rj dot equals 0, 1, minus 1, 0 times Rj, and the trace here is 0. So the trace squared minus 4 times the determinant is positive. So this is negative. And indeed we had oscillations, but since the trace was 0, alpha was 0, and this is just 1. There is no growth or decay, so this is a closed orbit. Okay? So the closed orbit is a special case for out of the spiral. Okay, we don't have much time left, but I will start the kind of summary of these things. Can I move the board from here? Yeah. We saw that in the examples that I showed you of the saddle and the node, which could be a star or it could be stable or unstable, we saw that the behavior depends on the eigenvalues. Also for the spirals, we saw that complex eigenvalues give us spirals. So we'd like to sum it up and have some simple rules or scheme in order to judge the stabilities of fixed points, of our fixed point at 0, 0, at the origin. So first I'd like you to note that if we are talking about dependence on eigenvalues, we can move to talking about dependence dependence on tau and on delta. So tau is just lambda 1 plus lambda 2, and delta is lambda 1 times lambda 2. Okay?
Like the trace and determinant.
Yeah, these are the trace and determinant. Okay, this if we can still see here, we have this quadratic formula that can show you that this is true. So we would like to create a classification of the fixed point at the origin based on the trace and determinant of the matrix. So I'm going to draw this plane, the trace determinant plane, and look at different cases on this plane. Okay, first of all, let's look at lambda 1 and lambda 2 are positive. I showed you before that this means that the fixed point will be unstable. There will be growth along both eigenvector directions. So this corresponds to this. Both tau and delta are positive. Right? Tau and delta are positive. This quadrant. So we have unstable points, unstable nodes, you could say. And I can make a little drawing where everything goes out of the fixed point. Now, the second case I would like to consider is both eigenvalues are smaller than 0 or negative. So here, tau must be negative, but delta is positive. And this is this quadrant here. And this is the condition for the stable node. Everything is going into the fixed point. Now what happens if lambda 1 is positive, lambda 2 is negative, or vice versa, right? It doesn't matter. So we don't know anything about tau yet, but we know that delta must be negative. And this is the case that we saw here. So all of this half of the plane is occupied by saddle points. This looks like this. These will be the eigenvector directions. The eigenvectors will serve as stable and unstable manifolds. Okay. And now for our special cases. We said that if we have complex eigenvalues, then we have spirals. And we had the condition was that tau squared minus 4 delta is negative. Tau squared minus 4 delta is negative. This means that tau square, delta is larger than tau square over 4. Okay? So for all points satisfying this condition, we will have spirals. And I can draw this curve here. This will be delta equals tau square over 4. And in this range above the parabola, I can have spirals. They will be unstable if they belong to this quadrant. Unstable spirals. And they will be stable if they are here. And this is a general classification. So if you get a two-dimensional linear system, then immediately you can convert it to the matrix form, and then find the trace, find the determinant, and see if this combination of trace and determinant falls in the saddle point area, or in the unstable node or unstable spiral area, and so on. So you